Hello everyone, I'm very pleased to give a talk on robot learning. The topic of my talk is to train intelligent agents to manipulate generic objects in daily life, and we will focus on 3D deep learning methods. In the next 30 minutes, we will introduce a large-scale 3D dataset for manipulation learning, some 3D deep learning-based methods to learn manipulations and affordance, and we will also discuss the new version of the SAPIEN physical simulator with state-of-the-art sim-to-real domain adaptation performance. Object manipulation poses many challenges to the machine learning community. First, when the agent manipulates objects, it is usually posed as a task to achieve certain goal from an initial state of the environment. To transform the initial state to goal states, policies may have to generate a long action sequence. When we search for the trajectory, we often do not know if it is correct until we reach the final goal. The second challenge is caused by the diversity of the environment. For example, the manipulation policy of humans are robust to many nuisances of the environment, including object topology, geometry, material, texture, etc. And this poses challenges in both finding the right policies as well as generalizing learned policies to test environments. Unlike vision and NLP models, which are trained and evaluated on highly diverse datasets, in manipulation research, datasets still lack diversity. The topics in this talk are picked around addressing these challenges. It is straightforward and reasonable to model the long sequence in a hierarchical manner. For example, in the reinforcement learning literature, hierarchical RL or HRL has been popular in the past few years. In HRL, the high-level policy generates a high-level action plan, which is to solve several subtasks. And these subtasks are also called options or skills in literature. For each subtask or option, it is solved by a learned or predefined low-level policy. It is worth emphasizing that this hierarchical decomposition of the policy into a high-level one and a low-level one is automatically emerged through many trials and errors of achieving the final goal in HRL framework. While HRL is shown to be effective on some difficult tasks, in general, the emergence of skills by training hierarchical RL algorithms is extremely difficult. The success rate is low, and the sample complexity is usually high. On the other hand, according to experiments, if the low-level policy is available, it becomes a much easier task to learn a high-level policy to coordinate low-level policies on long-horizon tasks. In addition, while there are all kinds of long-horizon tasks, the composition units, low-level policies, form a much smaller set. And this comes a natural idea of focusing on learning low-level policies reusable across environments and if we make an analogy across computer vision and robotics, which are two fields I work on, scene understanding and manipulation learning are tasks that require global understanding, while object recognition and skill learning are local tasks. From learning perspective, learning low-level policies can help generalization. By first learning the module to solve local tasks, we can recompose the local task solvers for global tasks. And this allows us to address novel unseen global tasks that are reconfigurations of local tasks efficiently. Next, let me present a manipulation skill benchmark and an open challenge based upon the benchmark built by my lab in collaboration with Berkeley and Stanford. This work has been accepted by the NeurIPS this year. The challenge is called SAPIEN Open Source Manipulation Skill Challenge, or ManiSkill Challenge for short. Our challenge runs in a virtual environment empowered by SAPIEN, which is a robot simulator developed by my lab. Our manipulation skill challenge has 5 key features. It is object-centric. We promote object-level generalizability. The agent in the challenge need to act based upon the 3D input in the form of point cloud or RGB images, and we provide large-scale demonstrations. And finally, the challenge is easy to get started for researchers, and we have open sourced all the resources. Next, let me give you more details. First, our challenge organizes manipulation skills in an object-centric manner. We first select a category of objects to be manipulated. Given the object category, we identify common manipulation tasks. For example, we may need to open the door of a cabinet. We may also need to pull out the drawer of a cabinet. And note that our object-centric skill organization allows us to leverage existing 3D object data sets, which are also organized by semantic categories. And this is indeed different from how the robotics community organizes skills. In a robotics paper, you may notice grasping as a skill, and experiments will verify whether the agent can grasp any graspable object, like an apple, a cup, a bottle, or even a plate. In contrast, our object-centric formulation restricts the generalization at object level, which reduces the difficulty of the problem. And let me be more specific about this point. By object-level generalizability, we mean that the agent needs to handle variations within an object category, which might involve topology, geometry, material, texture, illumination, and so on and so forth. And here is the skill of cabinet door opening, which requires to open the door of all kinds of cabinets. Similar as object recognition challenges, our test objects will be from the same category of the training objects, but they are different object instances. For the 2021 version, our challenge focuses on 4 carefully selected tasks covering common challenges of manipulation skills. And next year, we're planning to add more. We show 2 examples next. In the open cabinet task, a robot arm learns to open the doors of cabinets. The robot arm is installed on a movable platform, and the initial state of the gripper is not far from the object of interest. The robot takes the visual observation of the object as input and needs to change the state of the object in front of it to a desired goal state. Note that a door is installed on the Revolute joint, and here the robot opens the door to the extent larger than the pre-specified angle. We use success rate to measure the performance. In the push chair task, 2 robot arms need to collaborate and push the chair to a target position. And this chair is a swivel chair, and the seat could freely rotate about the base. And these are wheels installed on the base. Controlling the movement and direction of this system is not quite easy. In control theory, this is called an underactuated system, which is difficult to set up to manually design control. The second feature is that our challenge takes 3D visual input, which are RGBD images or 3D point cloud input. For the challenge this year, the point cloud is captured by a perfect depth camera to reduce the difficulty and help researchers focus on the key algorithms. But next year, we plan to use more realistic depth images. And we will revisit this point at the end of this talk. Various computer vision models can be applied. Our third feature is that for each object to be manipulated, we provide 300 demonstration trajectories. We used OpenAI Gym-like data protocol to provide demos. Note that the whole process is implemented by the routine with full physics simulation support. In the end, we have collected 63,000 demo trajectories in total, and since each demo has many transitions, this gives in total 1.5 million 3D video frames. So this challenge is also a large-scale 3D learning challenge. And here, we explain how to build a large-scale demonstration dataset. A popular approach is through crowdsourcing, that is to have humans annotate the demos. However, demos are trajectories which are hard to annotate, and in fact, the action space of our tasks are high-dimensional vectors that involve many robot joins, and the skills can be very tricky, so manually labeling demos is extremely difficult. Is it possible to collect demonstrations automatically without human annotation efforts? Ideally, we'd like to train our policy on all our environments together, but we also find it to be extremely hard. To solve our open cabinet task by reinforcement learning, we try to train an SEC with 1 million samples in SAPIEN. We can see that we achieve 100 success rate to open just a single cabinet. However, when we try to increase the variation in the training set, the success rate drops quickly to 0%. And this is because the large state variation caused by the diversity of the sets in our environment requires extreme overfitting ability of the network. Therefore, instead of training a single RL policy for all environments, we take the divide and conquer approach and solve each task independently. In this way, we have obtained the policy for each environment. The fourth feature of our challenge is that it's easy to start with. To accommodate for participants with different backgrounds, our challenge is arranged into 3 tracks. In the no interaction track, participants are only allowed to use provided demonstrations to build agents, and no interaction with the environment is allowed. We have provided a basic SDK, and the vision researchers without any robotic background can easily work on this track. In a no additional annotation track, both demos and interactions with the environments are allowed, but no external annotations is allowed. This is a track like the common setup of RL. And in the no restriction track, participants are encouraged to solve the problems using any method. Note that the method must work for robot objects that the algorithm have never seen before, which is really not. We have also imposed an open source policy for all the teams to attend our challenge. Next, let us show the baseline results for solving the manipulation scale challenge using popular vision and policy learning methods. Here, we evaluated some 3D deep learning network architectures in the imitation learning and the batch reinforcement learning frameworks. First, we show the results on a simplified setup. We pick a single object of the drawer opening task. We also assume that the test object is exactly the training object. However, it does not mean that the task is extremely simple. First, the input data is 3D, and second, when we test, although the object identity does not change, the initial state at the test time may be different from training time. So this is to test the generalizability across initial states given the same scene geometry. And we see that, first, having more demos are helpful. In fact, it is possible to achieve pretty high success rate with 1,000 demos for the object to manipulate. And second, transformers that can better capture regional dependencies are helpful. And finally, it's a bit surprising that batch RL could not outperform the simple behavior cloning method. We hope more batch RL experts could check and find better approaches. As a side note, the demos we provide are all successful demos. We just evaluated the generalizability when the test and the training object is the same single object. Here, we show a case when the test object is different from the training objects. This is trained on dozens of objects and tested on dozens of objects. And note that for each object, we have 3 demo trajectories, and each trajectories include at most 200 frames. So the total number of 3-point frames are at scale of a million. And we can see that it's a much harder task. None of known methods can perform reasonably well. We encourage everyone interested in this problem to participate and push this direction. And finally, thanks to our sponsor of Qualcomm AI research, the Manipulation Scale Challenge will be giving out monitor awards based upon performance and team diversity. The challenge of this year is almost over. Our resources are open online, including the challenge environments and the codes for the baseline approach. Welcome to check. We will also hold the second ManiSkill Challenge next year, and welcome to attend. Next, I will ask my students to introduce an algorithmic work relevant to manipulation skills and the SAPIEN, new version of the SAPIEN. Thank you.
Hi everyone, I'm Kai-Chun. Today I'm very happy to present to you some of my recent works on self-supervised affordance learning for manipulating articulated 3D objects. The space of 3D articulated objects is exceptionally rich in their myriad semantic categories, diverse shape geometry, and complicated part functionality. Future home assistant robots need to accomplish a wide and diverse range of household tasks in unstructured human environments. It is thus an important yet challenging task to develop autonomous agents that can perceive and interact with articulated 3D shapes as easily as we humans could do. Today, I will cover two works to give you examples how to bridge the perception interaction gaps by learning task-specific affordance maps. In Where to Act, we learn agent-object manipulation affordance given different action types, say pushing or pulling. While the O2O afford work extend the framework to learn object-object interaction affordance. Both works learn manipulation affordance as geometric preconditions of manipulation skills. For example, given this cabinet and the skill of pulling open the door, we predict where the skill could be applied, namely the geometry condition affordance map, and what action trajectories the skill policy will use, namely the geometry condition action trajectories. Different from previous work that learned such affordance using human annotation or demonstration, we will show how to leverage the state-of-the-art physical simulation and collect hundreds of thousands simulated trial and error interactions to achieve self-supervised learning. Requiring no human annotation or demonstration, we learn task-specific representations for different tasks and support large-scale learning regarding both large spaces, shapes, and tasks. For the first work, Where to Act proposed a self-supervised learning framework for agent-object manipulation affordance. Imagine that you are presented with this cabinet with an articulated door and drawer, given some primitive skills such as pushing, pulling, twisting, etc. We predict dense per pixel visual affordance heat maps for the skill preconditions. Then for each actionable pixel, we further propose a diverse set of gripper orientations for initializing the action trajectories. Our system takes either a 2D image or a 3D partial scan as the input and leverage state-of-the-art backbone feature extractor to obtain per pixel or per point features. Then for the output, we firstly decode an actionability score at this pixel, answering the question, is this action type good for this point? Next, a second decoder formulated as a conditional generative model proposed diverse gripper action directions. Finally, we learn an action scoring module to rate each action proposal with a score between 0 to 1. During the training, the third module can be directly supervised using the simulated interaction data with binary cross-entropy loss. We train the second module to produce distribution output trained over sparsely sampled interaction data points. For the first module, we indirectly supervise it given the other two network predictions and regress the output to the expected success rate executing a random proposal. For collecting the simulated interaction in SAPIEN, we hand code task-specific short-term interaction trajectories for the skills and parameterize them with the initial contact point and gripper orientation. In the scope of this work, we only study short-term tasks by using a task success threshold 0.01. Random data collection usually produces very few positive data, which causes severe overfitting during training. We thus propose an online data sampling strategy to address this, which essentially tries to collect more positive data by querying likely successful pixels predicted by the training networks. The second work, 02004, further extends the self-supervised affordance learning framework to predict object-object manipulation affordance. For example, to fit a bucket into a cabinet, we need to place it on shelves that are flat, having enough room, and providing enough height. This is our predicted object-object affordance heat map, from which we can immediately rule out the second shelf of this cabinet since the gap is too small to fit the given bucket. The downstream robotic task planner will benefit from this information because it only needs to consider the other three possible shelves. Then, our predicted affordance also predict where the bucket is likely to be placed. This also helps the downstream robotic planner to prioritize these highlighted locations for planning and searching. There are various object-object interaction tasks in our daily lives. We consider four scenarios in this work and design a unified framework to learn task-specific O2O affordance for them. For each task, given a 3D scene and a 3D object, we predict task-specific O2O affordance maps to indicate where could the 3D object interact with the 3D scene to accomplish the task defined by some task-specific success metrics. Our framework is able to unify the task inputs, outputs, environment specifications to handle various O2O interaction tasks. Our O2O afford system takes as input a partial scene scan, shown in blue, and a complete acting object point cloud, shown in red. We first employ two pointed plus network to extract per point feature maps over the two input data. Next, the proposed object kernel feature query module carries the explicit shape of the acting object over the scene geometry and queries feature maps over the acting object point cloud at a subsample set of locations from the extracted scene feature map. We combine the two parts of the features on the acting object point cloud and then employ a pointnet encoder that aggregate along the point dimension to obtain a global vector summarizing the joint information between the acting object and the scene geometry at this interacting location. Combining with other two feature sources from the scene and the acting object point cloud, we finally predict a scalar value within 0 to 1 for the affordance labeling at the current position. To obtain the per point affordance labeling over the entire input scene geometry, we interpolate the estimated affordance labels from the subsample seed points. We train our model on large-scale partner mobility dataset and achieve good results in both works. We also obtained reasonable results if directly testing the models over real-world scans or images. Of course, our works only made first step towards automating affordance learning without supervision, and there are many limitations for future works to address. Thank you for watching.
Finally, since a lot of experiments we just presented are done in simulators, you might have questions about whether we can train algorithms that can transfer from simulators to real environments. We will discuss this problem next. Our goal is to find a physical simulator that can support a transfer of policy learning. And this is our latest work to push the new version of SAPIEN 2.0 released recently. And this part will be covered by my student Fan Boxiang.
SAPIEN is a simulation platform for vision, learning, and robotics research. In its first version, SAPIEN supports physics and robotics simulation, rendering, and provides a large set of assets of articulated objects. The physical simulation in SAPIEN is designed to closely resemble the real world. As shown in this video, the robot in SAPIEN Simulator on the left is executing the same trajectory as in the real world shown on the right side. The simulated objects are manipulated through contact and friction forces, and the robot uses a PD controller to follow the trajectory just like in the real world. On the other hand, the large-scale simulation assets allow SAPIEN users to design many manipulation tasks. For example, in this video, SAPIEN assets are used to construct a large-scale manipulation scale benchmark for household tasks. Now, we introduce the next version of SAPIEN, SAPIEN 2.0. In this version, we further extend SAPIEN to include motion planning, improved rendering, accurate depth sensor simulation, and an extensive UI system. Let's start from the renderer. On top of this real-time renderer provided in SAPIEN 1, SAPIEN 2 has allowed unlimited number of shadow casting lights and ambient lighting from environmental maps. The renderer is now implemented in Vulkan with customizable shader pipelines and render targets, such as albedo, normal, and depth. If you want to render photorealistic images, SAPIEN also comes with a ray tracer, with an optional denoiser when using an NVIDIA GPU. The ray tracer also enables realistic depth sensor simulation through active light. To look at this simulation, let's first zoom into the robot camera. Similar to a real sensor, we project a light pattern onto the scene and use stereo vision to compute the depths. With ray tracing, our renderer produces realistic artifacts caused by occlusion, translucency, and specular materials, resulting in a realistic depth. Let's move on to our motion planning library, MPLib. Here, we first instruct the robot to move its face to the designated position. Next, we instruct the robot arm to move to its grasping position. We show the trajectory planned by MPLib with collision avoidance on the left and no planning on the right. And finally, we instruct the robot to place a plate onto the table. MPLib takes the robot model and its scene point cloud to avoid collisions and plan the trajectories. It is a simple and powerful tool that can be integrated into many manipulation tasks. Next, let's move right on to a showcase of the convenient SAPIEN viewer. Here, we can easily navigate around the scene with a mouse and keyboard, or focus on objects. It also provides annotations for object pose, joint axis, and camera placement. We can select here to view rendering modalities like normal and segmentation. When we select an object, we can find its physical and visual properties right here and easily see its collision shape. When working with the robot, the viewer allows viewing and editing joint angles and joint controllers. It also contains a built-in inverse kinematics solver, so we can easily change the pose of the robot. We can also easily edit the scene, such as moving objects around and moving the lights. The best part of this viewer is that all its functionalities are coded in Python, so it allows endless possibilities in customizations. Now, let me introduce some concrete use cases of SAPIEN. SAPIEN has been applied to design human teleoperation systems, manipulation benchmarks, transferable vision models, and robotics education packages. In the first example, the users have customized the SAPIEN viewer to allow using human hands to control the simulated robot. This allows them to conveniently collect data for imitation learning. Next, SAPIEN assets have been used to construct the SAPIEN Manipulation Skill Challenge, or ManiSkill, to test the generalizable manipulation across objects. It features visual point cloud inputs and physical interactions. ManiSkill Challenge also includes large-scale demonstration trajectories collected through reinforcement learning environments built with SAPIEN. Next, SAPIEN has enabled 3D vision models trained on simulated data to transfer to the real world, thanks to the realistic depth sensor simulation. Here, by generating training data in SAPIEN, the post-estimation model directly transfers to the real world without any fine-tuning. Finally, the rich robotics support and simple API make SAPIEN suitable as an educational platform. that's been used in multiple courses to let students gain hands-on experience with robotics control and planning algorithms. To summarize, SAPIEN supports realistic physics and sensor simulation, provides rich assets and convenient interfaces. It enables many downstream applications. You can try out SAPIEN with pip install SAPIEN on any Linux system.